So I'm going to, in this talk, I'm going to give a quick overview of the latest lineup as a whole. And there's a couple new things I'm going to introduce. So the first one is ultra-compact low-power processor, 22 series, talked about earlier. And also, since we are pushing for P-extension, DSP, SIMD-ISR, so we're going to talk about processor or implement that. And also, we're going to talk about the processor support multi-core cache coherency. So this is just for completion of the presentation. So this one you already see this morning. So I go to this. So from the bottom, we have a slim and efficient core two-stage pipeline, can running up to 800 megahertz at 28 process, and it's basically a very efficient one. And we implement V5 and V5E, which is 32 or 16 register. And we are also working with the partner for DSP extension and floating point as well. And going up, we have 5-stage pipeline core, which is fast and compact core with floating point, or DSP, or optional. And going up, we're adding with MMU, so running Linux. And then going up, we have a core running up to four of the core in parallel with cache coherency. So the core with X is for 64-bit. So otherwise, they are the same. So they have a very uniform feature: local memory, branch prediction, vector interrupt, and so on. And so this is another view. So just kind of line up the whole thing there and a different feature. And we're going to focus on N22 and DSP feature and multi-core. And again, this one we already went through this morning. So just to show all the extensions that we added, and some of them we're going to incrementally kind of pushing back to a standard. We cannot do it all at once because just the cache management feature, if you look at the mailing list, there's a lot of things to discuss there. So it takes time. So we would kind of gradually to pass back to the foundation. Right now, like Kevin also talked about this morning, we are focusing on coding the fast interrupt and also P-extension. Okay, and 22 series, code name is Bumblebee. So this figure means we intend to use it in entry-level MCU, which just have one processor for it, or you can use many of them in a large SoC, which we already have customers looking into that. So N22 is V5 or V5E, which basically maps to a RISC-V is E or I and MC, and a V5 extension. So 32 or 16 register. Two-stage pipeline, single issue, HP light, bus, and wait for interrupt and wait for event, which is one of the things that we added. So the pink one is the kind of the baseline, the default. And we provide a lot of options there, from PMP up to 16 entry, and UMO is also optional. Multiplier can be fast or small, and bridge prediction static or very simple dynamic, but also can help the performance. And local memory up to 512 megabytes. So because we encounter some customers like to use that address space for different purpose. And there's an instruction cache up to 32K direct map or two-way set associative. This is also, we think, very important. We directly support how to handle misaligned load store. Again, I like to kind of raise the awareness of that because today, majority of open source code running on x86 or ARM, and both architectures support misaligned access. So if you are unlucky, you porting code from those two architecture to any architecture don't support misaligned access, you're going to get a lot of exception and spend time to do emulation, you're going to kill your performance. 22 series support both click and prick. Definitely you may not use both, but click is for local interrupt, can opt to over 1,000 sources, 250 priority, and selective vectoring with priority preemption, and efficient software tail chaining, which Kevin talked about this earlier. And prick is both for the interrupt sharing at the platform level. So when you have multiple core and multiple N22, and you want to distribute the interrupt across the different 22, and it can be used. And also for SoC flexibility, we support additional interfaces on SoC. It has APB-based private peripheral port, and also fast I/O port with single cycle latency. And a standard JEDEC debug module up to 8 trigger, and also support both 4-wire and 2-wire. And 2-wire is very important for entry-level MCU, where ping is a testing cost. And other advanced features like PSP, FPU, and AC for custom extension is on the way. So here we should look at some performance. Earlier I mentioned at the 28 nanometer, the frequency can go up to 800 megahertz. That on some configuration. And minimum gate time is less than 15K gate, which actually can be smaller. And base core mark is very close to 4. And DMIPS with the ground rule, no inline, is 1.8. Compared to the CPU A and CPU B, which you probably know what it is, because N22 is very configurable, so we configure it so that it's kind of matching the capability with those 2 core. You can see we list the data here. One thing, when people using open source like LV or GCC to compare with the commercial processor, they usually using the GCC of that commercial processor. But usually the other company, GCC is suck. So if you want to really do a fair comparison, you should compare to their the best compiler. So here we use that. So compare with CPU A, which is V7M, you can guess what it is. And we have a full configuration, which AndeStar V5. So we have for core mark, we have about 20% margin over that CPU. And in a smaller configuration compared to another smaller core, is about 24%. So it's very good. And dry zone is even better, but dry zone you can use as a reference because it's a very small benchmark. And for code size, again, we are not comparing with the other guy using GCC. We're using their commercial compiler. So code size, we are smaller compared to the CPU A. And CPU B, code size is very similar. Okay, so this is very good data. Okay, now let's look at 25 series processor with DSP capability. So we have a couple of them, including 32-bit D25F and A25 and A25MP, and also X25 and X25MP, which is 64 bits. So the P extension has a 64-bit version and also 32-bit version. Those who look at Andy's presentation in the past, so this is already appeared before, just want to highlight that at 28, we have different configuration of the core, but they are all full featured, including 32K caches, branch prediction, single precision or double precision floating point with MMU. And the frequency can range from 1.2 gigahertz to 1.4 at 28 nanometer. And today we're going to show you the first implementation of P extension drift. Here I want to highlight some of more powerful instructions from the P extension. So in the SIMD version, you can have, for example, up to 4 A/A multiplication, and then write the result to 16-bit storage. And also, or you can have 2 16x16. And in the partial SIMD, which is basically means accumulation, so you can do more actually. So you can do for 32-bit RV32 CPU, you can do 4 A/A multiplication, and for RV64, you can do 2 sets of that, and the result accumulating to 32-bit register. And or you can do 2 16x16 multiplication with accumulation for 1 set. And if you are RV64, then you can have 2 sets of that, doing that in parallel. And there's also RV64 only instruction. So that is to do 2 32x32 multiplication with 64-bit accumulation. And they have respective different cycle latency, 1 cycle, 2 cycle, and 3 cycle, depending on the computation. So how does those instructions help your application? So for DSP, we develop and optimize so-called DSP library for both RV32 and RV64. And they have over 200 of them. We categorize them into 8 different of them. So they range from, let's say, basic, complex number, control, filter, matrix, statistic, transform, and utility. So so each one has their own different speed up versus if you don't have DSP, because we also have non-DSP library, because some customers actually already are using that in the past. And if you average all of them, assume each category has the same percentage. So we can say that RV32P extension can, on average, provide 2x speed up, and maximum go to over 5. And for RV64P, you bring over 2.5 speed up on average. The maximum is over 10. And usually, because DSP has a very wide range of them, some of them is not really SIMD friendly, but you can expect those who are more popular to inner product, filter, and also metric multiplication and so on. Those can get quite good speed up. So those DSP library is very similar to what ARM or TI, ADI has. So it's very common DSP functionality. So beyond DSP library, so let's look at some speed up for some application. Here we use RV64P for the CFAR10 image classification and also PNet face detection. And so they can get to almost 11x speed up or over 7x speed up. And for RV32P, we position it to handle the speech or voice codec. For MR, it can go over 3x speed up, and MP3 is simpler computation, so close to 2x speed up. Next, let's look at A25MP and X25MP. That is multi-core with cache coherency, both 32-bit and 64-bit. This is kind of over high-level block diagram. So in this MP subsystem, you can have up to 4 CPU of A25 or X25 with the feature that we talked about, and also they support Linux SMP. And in the bus interface side, from the top, you can see it support a local memory slave port, so DMA can connect to that slave port and direct write to the core of your selection to the local memory, both instruction or data. And that brings very good interaction with SoC, especially for real-time control. And there's also coherency slave port, which allow you to connect the bus master without caches, but you want to make it coherent. And also down the bottom, you have XI bus master interface with frequency range of different clock ratio. And then on top, you have platform level interrupt controller for interrupt handling and standard debug and trace support. So the coherency is basically based on MACI, the unit we call AndeStar coherency unit, or ACU. MACI protocol, and use duplicated tag, and again, IO coherencies for the cache-less bus master. And in the MP subsystem, there's also L2 cache controller, which is optional because it can be quite big but bring good performance to you. So this size can from 1 to 28K into 2 megabyte, and line size 32 byte, and it provides to 16 weight associativity with random replacement and also write-back replacement policy. But here we put some effort for SRAM optimization because SRAM, if you want to put a large L2 cache, it can be expensive. So usually customers want to choose a high density one, and which will be slow. So cache SRAM access cycle we configure, so we let user to configure, so 2 cycle and above. And for the performance reason, so we do the bank interleaving. So for the tech bank, we provide 2 bank, and for data bank, for data, SRAM we provide 8 bank. So with that, pipeline can be fully kind of go smoothly if you don't have contention. And L2K controller also support software managed operation. Like you can write back a line or you embed a line for a particular purpose. And it provide, again, optional ECC error protection, which is the same as L1 cache. And also it provides the prefetching. So for instruction, it's basically you can control it so that after you miss 1 line or 2 lines sequentially, and you would automatically do the prefetch. And for the data, basically it can continue to watch 8 different address sequence, and then based on again selected misses, and it will start to do a prefetch. So either 2, 4, 8 lines. So in the Linux, so this kind of configuration, we actually already have customer. Some of them want running Linux, some of them want to make it kind of running bare metal or running RTOS, but not Linux environment. So for Linux capable configuration, with RV64, 32 kilobytes instruction and data caches, 256 entry BTB, 128 entry shared TLB, and also entry micro TLB, entry PMP. And it can running around, at this point, it's running about 1 gigahertz at 28. And again, this is the worst case, worst corner. And the size, the gate count, the core itself is about 200 kg. And ACU L2 is a little less than 200 kg. Okay, so in conclusion, Andes is working hard to catch up the demand from our customer. So they're asking us to provide more RISC-V processor faster. So about our offering from 22 series, ultra compact and low power core, which we work with partner nuclear. So next session, Tony will talk more about it. And 25 series is, we started with that, so it supports 32-bit, 64-bit, and it has many configurations. So it can be used as fast and compact, but also full feature running Linux SMP. And DSP ISA is kind of emerging need we kind of get from customer, and so they require the building data processing capability. So we quickly put that together with very good performance and full support from the library and as well as a compiler. And this custom extension is also always there, so we're supporting it for our full line. So you can use conjunction as, for example, DSP instruction, implement the ring buffer, which I gave a talk in last RISC-V Summit. And so that's for kind of serve the growing demand for DSA. And we, as you can see, we kind of very active in doing the open source tool chain and contribute and so on. So we have strong tool development and also software infrastructure from Andes. But beyond that, we also work with partners like Imperis, Lauterbach, IR, and so on. So they are also spreading our CPU and our extension as well. And so far, our customers have been using our core for this application, which we talked about that earlier this morning. But again, AI, FPGA, IoT, MCU, security, storage, wireless. So Andes positioning us as trusted computing expert. And if you're serious about RISC-V, so I think we want to be your best RISC-V partner. Thank you.